Tonight, we'll look at galaxies the way the universe gives them to us, as light that has been traveling for a very long time. In a quiet sense, every distant galaxy is already a kind of memory. And the facts we'll share are simply small, steady ways to read that memory. Welcome. This is a calm space for astronomy where you do not need to hold on to every detail. You can let the ideas arrive gently, one at a time, and you can let them pass on when they are ready. We'll begin close to home with the Milky Way as a familiar reference. Then we'll widen the view. Slowly, our galaxy becomes one example among countless others. It helps to start with a simple definition. A galaxy is a long-lived system of matter held together by gravity. It is not only a collection of stars. A galaxy also includes clouds of gas and dust. These are the raw materials for future stars. They drift through the space between suns, shaping how a galaxy looks and how it changes. Many galaxies contain bright regions where new stars are forming. They also contain darker lanes where dust absorbs starlight. Even when nothing seems dramatic, a galaxy is always quietly evolving. Most galaxies also seem to live inside something we cannot observe directly. They are embedded in broad halos of dark matter. Dark matter does not glow or reflect light, but its gravity still matters. That invisible mass helps explain why galaxies hold together. It also helps explain why stars move the way they do, especially far from the center. The halo can extend well beyond the bright edge we see in images. Near the center, many galaxies have a denser region where stars are packed more closely. Some galaxies also contain a supermassive black hole at the core. Even when it is quiet, its presence can be traced through motion and structure. If you picture the Milky Way, you can use it as a gentle map for what a galaxy can be. It has a disk with spiral structure with gas and dust threaded through it. It also has a faint halo where older stars and clusters drift in long orbits. When we look beyond the Milky Way, we find these ingredients again and again. They are rearranged into many forms. The variety is part of the calm pattern of the universe. Some galaxies are graceful spirals with arms that sweep outward like slow currents. Some are smooth ellipticals, more like glowing clouds of older stars. Some are irregular, shaped by tides, encounters, or a crowded early history. Even these differences have a steady logic behind them. Galaxies are not fixed sculptures. They are systems that respond to gravity and environment over long spans of time. Time is also woven into the act of seeing them. In daily life, sight feels immediate. In astronomy, it is not. Light takes time to travel. The sky quietly records that travel time. When we look at the moon, we see it as it was a little more than a second ago. When we look at the sun, we see it as it was about 8 minutes ago. These are small delays, but they hint at something larger. Distance and time are linked in a simple way. A galaxy millions of light years away is seen as it was millions of years ago. A galaxy billions of light years away is seen as it was billions of years ago. So the farther we look, the farther back in cosmic history we are naturally reading. You do not have to calculate anything here. You do not have to hold a timeline in your mind. It is enough to remember one gentle relationship. Far away also means long ago. This is why galaxy facts can be told like a quiet story instead of a list. The facts connect to one another. They form patterns you can recognize without effort. A single idea, like gravity shaping a rotating disk, can explain many features at once. Another idea, like dark matter halos, shows up across many observations. And another, like galaxy mergers, helps explain why the universe contains such a range of shapes. As we move through this episode, the Milky Way can stay in the background as an anchor, but we will not stay there. We will widen outward to galaxies of many kinds, from small dwarfs to enormous giants. We will talk about how galaxies grow and change. We will talk about how they interact and merge, and we will place them inside the larger structure of the universe. The goal is simple. Each fact is a small point of clarity offered without urgency. You can let these ideas settle as a sense of scale and order. The universe is vast, but it is not chaotic. It has structure we can trace and histories we can read, and it follows steady physical rules across enormous distances. So, as we begin, imagine the night sky as depth rather than a flat ceiling of lights. Some of that light is near and some of it is unimaginably far, and within that depth, galaxies are the long-lived patterns that quietly endure. To understand what a galaxy is, it helps to picture it as a system rather than a shape. A galaxy is a region where gravity has gathered matter into a stable, rotating, evolving whole. The beauty is real, but the underlying idea is simple. Gravity is the quiet organizer here. Over long time spans, it pulls gas, dust, and stars into shared motion. Even when a galaxy looks still in a photograph, the stars inside it are always moving. Most of the galaxies we talk about can be described using a few basic parts. These parts are not rigid components with sharp edges. They are more like regions with different densities, ages, and kinds of motion. Many galaxies, including the Milky Way, have a disk. A disk is a flattened region where stars and gas orbit in an organized way. In spiral galaxies, it is also where you find spiral structure, dust lanes, and much of the ongoing star formation. Inside the disk, the gas is not spread evenly. It gathers into clouds, and those clouds can collapse into new stars. This is why disks often look bright and textured, with blue star-forming regions and darker bands of dust. Closer to the center, many galaxies have a bulge. A bulge is a more rounded, denser region filled with many stars. The stars there often have different kinds of orbits, less like a flat wheel and more like a crowded, three-dimensional swarm. Bulges tend to contain older stars on average, though there are exceptions. They can also hold star clusters, and they often sit around the galaxy's central region. If a galaxy has a supermassive black hole, this is where its influence is most strongly felt. Around and beyond the disk and bulge, galaxies extend into a halo. The halo is faint and diffuse, and it can be hard to picture because it does not look like a shell. It is simply a broad region where stars, star clusters, and gas can exist far from the bright center. Some halos contain old globular clusters which are dense balls of ancient stars. Halos also contain the long, thin stellar streams left behind when smaller galaxies were pulled apart. These streams are one of the gentle ways the sky keeps a memory of past mergers, but when astronomers speak of a halo, they often mean more than the faint visible one. They also mean the much larger dark matter halo. This is the invisible structure that appears to surround the galaxy and dominate its mass. You can introduce this idea without making it heavy. The reason dark matter enters the story is not because scientists wanted a mystery. It enters because the motions inside galaxies do not fully make sense without extra gravity. If you measure how quickly stars orbit at different distances from the center, you find a surprising pattern. Far from the center, the stars often keep moving fast. They move faster than you would expect if the galaxy contained only the mass we can see. In a simple picture, you might expect the outer stars to slow down. You might expect the gravity to weaken in a way that lets the edge drift apart. But in many galaxies, the outer regions remain tightly bound in motion. The calm conclusion is that there is more mass than light. Something adds gravitational pull without adding glow. This extra mass behaves like a broad, extended halo, and we call it dark matter. Dark here is not a mood, it is a description of interaction with light. Dark matter does not emit light the way hot gas does, and it does not reflect light the way dust can. It is detected through gravity, through the way it shapes orbits and bends light. This invisible halo matters because it changes the scale of what a galaxy is. The bright disk might be 100,000 light-years across, but the dark matter halo can extend much farther. In a sense, the visible galaxy is nested inside a larger gravitational landscape. Once you have that foundation, the main types of galaxies begin to feel easier to hold. The categories are not perfect boxes, they are more like broad families, shaped by formation and history. Spiral galaxies are the type many people picture first. They have disks and many have arms that curve outward in a pattern. These arms are not rigid structures like painted lines. They are regions where stars and gas tend to be denser and where star formation often occurs. Spirals often contain a mix of stellar ages. They can have young, bright stars in their disks and older stars in their bulges. Their gas and dust give them texture, and their rotation gives them a sense of organized motion. Elliptical galaxies look different. They are often more rounded and smooth without obvious arms or dust lanes. Many ellipticals contain older stars, less cold gas, and lower current rates of star formation. Their stars move in a more randomized set of orbits. Instead of a single dominant plane of rotation, there is a broader range of motions. Ellipticals are common in dense environments like the centers of galaxy clusters, where mergers have been frequent over long times. Irregular galaxies do not fit the neat spiral or elliptical picture. Their shapes can look disrupted, lopsided, or clumpy. Sometimes that irregularity is the result of interaction, like tidal forces from a neighbor. Sometimes it reflects a smaller galaxy's inability to settle into a stable disk. Many irregular galaxies are rich in gas and can form stars actively. They can look like glowing fragments, but they are still held together by gravity in their own way. Then there are dwarf galaxies, which are smaller and fainter than the giants. Dwarf is a size category, but it also often implies a different kind of history. Dwarfs can have a few million stars or a few billion, and they come in multiple forms. Some dwarfs are dwarf irregulars, still forming stars and containing gas. Others are dwarf spheroidals, which are faint, gas-poor, and dominated by dark matter. Many dwarfs orbit larger galaxies as satellites, and some are slowly being pulled apart. This is one of the quiet truths of cosmic structure. Large galaxies grow partly by absorbing smaller ones. Dwarf galaxies are common, and they are important because they are both building blocks and witnesses. To place all of this into a calmer mental map, it helps to talk about neighborhoods. Galaxies are not scattered randomly in space like isolated lanterns. They gather into groups, and groups can gather into clusters. Our own neighborhood is called the local group. It is a small collection of galaxies bound together by gravity. The Milky Way and Andromeda are the two largest members, and there are many smaller galaxies orbiting within the group. You can think of the local group as a cosmic district. The distances are still immense, but the idea is familiar. It is a region where gravity is strong enough to keep galaxies in long-term association, even while the universe expands on larger scales. Andromeda is more than a beautiful smudge in long-exposure images. It is a full spiral galaxy with its own disk, halo, and satellite galaxies. It is also moving toward the Milky Way, and over billions of years the two systems are expected to merge. The local group also includes the Triangulum Galaxy, another spiral, and dozens of dwarf galaxies. Some of these dwarfs are easier to see from the southern hemisphere, like the Large and Small Magellanic Clouds. Others are extremely faint and were discovered only through careful surveys. This neighborhood framing matters for sleep-friendly understanding. It reduces the universe from an abstract infinity to a layered geography. There is our galaxy, then nearby galaxies, then larger gatherings beyond, each level connected by gravity. Now, as soon as we talk about galaxies, three words tend to appear: size, brightness, and mass. They sound similar, but they refer to different things. Keeping them separate makes the whole topic feel calmer. Size is about extent. It is how wide a galaxy's visible stars and gas spread across space. Some galaxies are compact, dense, and relatively small. Others have faint outer regions that extend very far, making their sizes difficult to define with one crisp edge. Brightness, or luminosity, is about how much light a galaxy produces. A galaxy can be large but not especially bright if it contains older stars and little new star formation. Another galaxy can be smaller but very bright if it is forming stars rapidly. Mass is about the total amount of matter, including what we can see and what we cannot. A galaxy's mass includes stars, gas, dust, and the much larger contribution from dark matter. This is why a galaxy can have modest visible brightness while still being very massive. These differences matter because they prevent misleading comparisons. Two galaxies might look similarly bright in an image, but one could be much farther away. Two galaxies might have similar sizes, but one could have far more dark matter. Astronomers measure these properties with different tools. Brightness can be estimated from the light received and corrected for distance. Size depends on how faint a galaxy's outer glow is and how far you can trace it above background. Mass is often inferred through motion and gravity. Rotation curves, the movements of satellite galaxies, and gravitational lensing all provide clues. In this sense, galaxies are not only seen, they are weighed by their influence. If you hold on to just one calm summary, it can be this. A galaxy is a gravitational system with visible structure and an invisible backbone. It has regions like disks, bulges, and halos, and it belongs to a larger neighborhood of other galaxies. And once that foundation is in place, the facts that follow become easier to enjoy. They are not separate trivia. They are examples of how these systems behave in different environments and across different times. In the next segment, we can stay close to this foundation and begin to explore how galaxies change. We'll move from what a galaxy is to what a galaxy does over cosmic time through growth, encounters, and the slow shaping of structure. One of the gentlest ways to notice a galaxy's history is simply to look at its light. Galaxies do not wear labels that tell us their age or their past. Instead, they carry clues in their colors, their textures, and the way their brightness is arranged. Color, in astronomy, is not mainly about decoration. It is often a quiet measurement of what kinds of stars dominate the light. And because stars change as they age, a galaxy's overall color can act like a soft summary of its recent story. When a galaxy looks bluish, it usually means it contains many young hot stars. These stars burn at higher temperatures and emit more light at shorter wavelengths. They do not live very long on cosmic timescales, which is part of why they are so informative. A blue tint is often a sign that star formation is active now, or was active in the recent past. It suggests that the galaxy still has cold gas available. It also suggests that the galaxy's disk, arms, or star-forming regions are still producing fresh starlight. When a galaxy looks more yellow or reddish, the interpretation shifts. Redder light is often dominated by older, cooler stars. These stars can live for billions of years, and they accumulate over time, becoming the steady background of a galaxy's glow. A red galaxy is not dead in an absolute sense. It may still contain stars being born in small amounts or in hidden regions, but overall, a red color tends to imply that the galaxy's most active star-forming era is behind it. Dust can complicate this picture, and that is part of what keeps astronomy honest. Dust can absorb and scatter blue light, making a galaxy appear redder than it truly is. So astronomers check the story using other wavelengths, such as infrared, where dust becomes more transparent. Still, as a first quiet guide, color is useful. Blue often means youth, gas, and ongoing creation. Red often means older stellar populations and a slower pace, shaped by time and by the galaxy's environment. Spiral galaxies are an especially good place to see this interplay between color and structure. In many spirals, the arms are highlighted by blue star-forming regions. The disk can show bright clusters and glowing gas, while the central bulge often looks warmer and more yellow. This contrast is one reason spiral galaxies feel so vivid. They are not uniform. They show multiple eras of stellar life in one system. layered together. The bulge can hold older stars, while the disk keeps producing younger ones. The spiral arms themselves are worth describing gently because they often look like solid features. It is natural to imagine the arms as permanent streams of the same stars, moving as a unit. But a calmer and more accurate picture is that the arms are patterns. A helpful analogy is traffic, because it captures the idea of a moving pattern without implying a rigid structure. On a highway, a traffic jam can form and persist for a long time. Individual cars enter the jam, slow down, and later leave it, while the jam itself remains as a pattern. In a similar way, spiral arms can be regions where stars and gas bunch up as they orbit the galactic center. The material moves through the arms, but the pattern can persist. The arm is not made of the same exact stars forever, even if it keeps its shape. When gas enters an arm region, it can be compressed. Compression encourages clouds to collapse, and collapsed clouds can form new stars. This is why spiral arms often have bright patches of young stars, and why they can look like glowing lanes across the disk. This density wave picture is not the only story for every spiral galaxy. Some spirals have arms shaped by interactions, by bars in their centers, or by local instabilities in the disk. But in many cases, thinking of arms as patterns rather than fixed objects helps the image feel both simpler and truer. Spiral galaxies can also carry a bar, a straightish band of stars through the center. Bars are common, and they matter because they can move gas inward. That inward flow can feed star formation near the center and can influence the growth of the bulge over time. Even in a calm discussion, it is worth noting that spiral galaxies are not frozen designs. Their disks can warp, their arms can shift, their star formation can brighten and fade. They are stable enough to last for billions of years, yet flexible enough to keep changing. Elliptical galaxies show a different kind of history. They are often smoother and less textured, with a light that fades outward in a gentle gradient. They usually lack obvious arms, and many contain little cold gas for new star formation. This is why ellipticals tend to look redder on average. Their light is dominated by older stars that have had time to accumulate. They can be immensely massive, especially the giant ellipticals that sit at the centers of galaxy clusters. Inside an elliptical galaxy, the motion of stars is often less ordered. Instead of most stars orbiting in a single plane, their orbits can point in many directions. Some stars move in elongated paths, some in loops, and the overall motion is more like a stirred swarm than a spinning disk. This does not mean the galaxy is chaotic in a destructive sense. It is still held together by gravity, and it can remain stable for a very long time. But it does suggest a history that may include mergers, because mergers tend to disrupt neat rotation. When galaxies merge, their stars rarely collide directly. There is far too much space between them, but their gravitational fields pull and reshape the overall structure, and the organized rotation of disks can be scrambled into a more rounded, elliptical form. Elliptical galaxies can also have halos of hot gas that glow in X-rays. This hot gas is not the cold star-forming fuel found in spiral disks. It is a hotter reservoir, often linked to the environment of galaxy clusters and the energy injected by past activity, including supermassive black holes. This is part of why ellipticals can feel like quiet elders of the universe. They can be huge and luminous, yet they often make new stars slowly. Their brightness comes from the many stars they already contain, rather than from fresh bursts of starbirth. Between the clean categories of spiral and elliptical, many galaxies live in transitional states. Some are spirals that are running low on gas and slowly reddening. Some are post-merger systems that still carry tidal tails or faint shells, like ripples left in their outer light. These subtle features matter because they show that morphology is not just type, it is also history. A galaxy's shape and color are records of what it has experienced, and what resources it still has available. Irregular galaxies and dwarf galaxies are especially useful here because they are sensitive. Their gravitational bindings can be weaker, and small influences can change them. In that sense, they can behave like laboratories for evolution. Many irregular galaxies are rich in gas. They can form stars in bursts rather than in steady rhythms because their internal structure is more easily disturbed. A close pass by a larger galaxy can pull on them, compress gas, and trigger new star formation. Some dwarfs are being pulled apart even now. Their stars can be stretched into streams, their gas can be stripped away, and their shapes can become more distorted over time. When you see a dwarf galaxy near a larger one, you are often looking at a fragile system in a strong gravitational neighborhood. Dwarf galaxies also matter because they appear to be strongly dominated by dark matter. Many dwarfs have far less visible matter than their motions would suggest. They behave as if they sit in relatively large dark matter halos compared to their starlight. This makes them important in the larger puzzle of what dark matter is and how it shapes structure. Dwarfs can preserve clues that might be harder to see in big galaxies, where many processes overlap. Their simplicity, in a way, makes them revealing. Now, there is another category that is easy to overlook because it is not about dramatic shape. It is about faintness. Some galaxies are so spread out that they are almost invisible against the background of space. These are often called diffuse galaxies, and some of the most extreme are called ultra-diffuse galaxies. The defining feature is not that they have no stars, it is that their stars are spread thinly over a large area, giving them very low surface brightness. An ultra-diffuse galaxy can be surprisingly large in size, sometimes comparable to the Milky Way in extent, yet it can contain far fewer stars, so its light is like a thin mist. If you placed one behind a bright sky, you might miss it entirely. For a long time, galaxies like this were undercounted because they are difficult to detect. They do not stand out as crisp objects. They require careful imaging, long exposures, and techniques designed to see very faint, extended glow. Their existence raises calm questions about galactic life. How does a galaxy become so spread out? Did it lose gas early, failing to form many stars? Was it puffed up by interactions, tides, or internal processes? Some ultra-diffuse galaxies appear to be strongly dominated by dark matter, which could help them remain bound despite their thin starlight. Others may have unusual histories that challenge the simple idea that galaxy size and galaxy mass always travel together. They are a reminder that the universe can contain real things that are easy to miss. A galaxy does not have to be bright to be significant. Sometimes the faintest systems carry the sharpest tests for our models. So when you see a galaxy image, you can treat it as a calm surface with depth underneath. Color hints at the age of its starlight and the presence of gas. Shape hints at its motion and its past interactions. And faintness can hint at a hidden mass that holds a delicate structure together. In this way, morphology becomes more than classification. It becomes a language. Spirals speak of disks, patterns, and ongoing star formation. Ellipticals speak of older stars, randomized motion, and long histories of merging and settling. Irregulars and dwarfs speak of vulnerability and change, of systems shaped by their surroundings. Diffuse galaxies speak of hidden structures and of how much can exist beyond easy visibility. And once you begin to hear that language, the next step comes naturally. Galaxies do not only grow in isolation, they meet, they pass, they merge, and they leave traces behind. In the next segment, we'll move into those interactions. We'll look at the quiet ways galaxies reshape one another over time, and how the larger cosmic environment guides their slow, patient evolution. Galactic encounters are sometimes described with words like collision and crash. But on the scale of galaxies, the calmer truth is closer to a dance. The forces involved are real and immense, yet the rhythm is slow. Two galaxies can begin influencing each other long before they ever overlap in an image. Their gravity reaches outward. It tugs on outer stars and on wide halos of gas. Over time, the galaxies drift into a shared orbit. They fall toward one another, pass, and swing back. This can repeat for hundreds of millions of years. What makes this feel so different from everyday impacts is the emptiness inside galaxies. Even a galaxy packed with hundreds of billions of stars is mostly space. Stars are separated by distances so large that direct star-to-star collisions are extremely unlikely. So when galaxies meet, it is not the stars that hit. It is the gravitational fields that combine and reshape. The visible structures respond like water responding to tides, except the water is made of stars. In the first close pass, the most delicate parts respond first. The outer disk can warp, the spiral arms can stretch, the halo can be pulled into a slightly different shape. Then something beautiful often appears. Long, faint extensions of light can be drawn out from the galaxies. These are tidal tails, and they are among the clearest memories an encounter can leave behind. A tidal tail is not a solid arm thrown outward. It is a stream of stars and gas that have been pulled onto new orbits by changing gravity. The tail can curve like a ribbon, sometimes reaching far beyond the galaxy's original edge. These tails can be so faint that they require deep imaging to see, but when they are visible, they carry a calm message. A tidal tail is a signature of interaction. Sometimes the encounter does not immediately produce a final merger. The galaxies can separate again, still bound, and return for another pass. Each pass can pull out more material and rearrange more orbits. With time, those long tails can become broader and more diffuse. They can drift and fade into the surrounding halo. Yet even as they fade, they remain as structure. This is why astronomers speak of stellar streams. A stream is a river of stars tracing an orbit that was shaped by an interaction. Streams can wrap around a galaxy like faint loops, outlining the geometry of gravity. In some cases, a stream is the leftover path of a small galaxy being torn apart. The small system is stretched, its stars pulled into a long, thin arc. The original galaxy becomes less distinct, while the stream becomes its footprint. These streams are subtle, but they are persistent. Because stars can orbit for billions of years, the pattern can remain long after the original event. The galaxy carries its history as motion and structure. This is one of the gentlest themes of galactic evolution. Nothing needs to announce itself loudly. A past interaction can remain present as a faint curve of light. A simple way to imagine it is to picture a stirred cup of tea. The stir itself is brief, but the swirl continues for a while. In a galaxy, the stir might be a close pass. The swirl can last for ages. There is also a kind of galactic cannibalism, though it happens without drama. Larger galaxies tend to grow by absorbing smaller ones. A small companion drifts close, becomes bound, and begins to lose material. The process is gradual. The smaller galaxy is stretched by tidal forces. Its stars are stripped away and added to the larger galaxy's halo. This is happening in many places across the universe. It is also happening close to home. One example, mentioned only as a bridge, is the Sagittarius dwarf spheroidal galaxy. The Sagittarius dwarf is a small companion of the Milky Way that is being pulled apart. Its stars are forming streams that wrap around our galaxy. It is a local illustration of a much more general process. The key point is not the Milky Way itself. The key point is that growth through accretion is common. Big galaxies often become big by collecting smaller systems over time. Another local bridge is the future merger between the Milky Way and Andromeda. It is often described as a collision, but it will unfold as a slow, gravitational choreography. The two galaxies will pass through each other, swing apart, and return. Their disks will be disturbed. their gas will compress. Over time, the system will settle into a new form. This kind of large merger is not rare in the universe's long history. Many elliptical galaxies are thought to be the products of multiple mergers, layered over billions of years. But mergers are not all the same. Sometimes a large galaxy absorbs a small one, sometimes two galaxies of similar size merge, sometimes a fast flyby leaves a mark without ending in full union. Each kind of encounter leaves different traces. A small merger might leave thin streams and a slightly puffed-up halo. A major merger can transform the entire structure. To understand why, it helps to separate stars from gas and dust. Stars mostly behave like a collisionless system. They pass by one another, and gravity reshapes their orbits. Gas and dust behave differently. Gas clouds can collide, they can compress and shock. They can lose energy by radiating heat away. This is where encounters can trigger star formation. When gas is compressed, it becomes more likely to collapse. Collapse can lead to the birth of new stars. In a merger, that compression can happen on large scales. Gas is funneled inward, clouds collide more often, dense regions form. Instead of thinking of it as fireworks, it can be calmer to think of it as waves. A merger sends waves of compression through a galaxy's gas. Those waves can become waves of star formation. A starburst galaxy is one where this process becomes intense for a time. The galaxy forms stars much faster than usual. It shines more brightly in ultraviolet and often in infrared because dust absorbs and re-emits starlight as heat. Starbursts do not last long by cosmic standards. They consume gas quickly. They also produce feedback as massive stars and supernovae heat and push on surrounding material. So a merger can create a bright phase and then a quieter one. The wave passes. The gas is used up, blown out, or heated. The galaxy settles. This is one reason mergers can change morphology. A spiral galaxy relies on an ordered disk. It relies on rotation and on a relatively thin distribution of stars and gas. A major merger can disrupt that order. The stars can be scattered into more random orbits. The disk can thicken, warp, or dissolve. If the merger is strong enough, the final system can resemble an elliptical galaxy. The light becomes smoother, the rotation becomes less dominant, the structure becomes more rounded. This does not mean spirals always turn into ellipticals. Some mergers are minor, some spirals survive, though altered. Some rebuild disks later if they accrete fresh gas. But the general trend is simple. Encounters scramble. Gas can be driven inward. Star formation can surge. And over time, gravity smooths what remains. There are also gentler forms of interaction that do not require full mergers. A close pass can pull on a galaxy's arms, stretching them into a symmetry. It can trigger local star formation without fully blending two systems. In galaxy clusters, where many galaxies share a region of space, interactions can be frequent. The environment can be busy, even if each event is slow. Over long times, this repeated stirring can change galaxies. Disks can be heated and thickened. Gas can be stripped by the hot medium in the cluster. Star formation can decline. But even here, the mood can remain calm. The universe is not rushing toward drama. It is following gravity and motion. When astronomers simulate these interactions, they often see the same quiet sequence. The first pass raises tails and bridges. The galaxies swing apart. The second pass deepens the distortion. Eventually the cores merge. The system relaxes. The outer material continues to orbit and settle. The tails fade, but traces remain in the halo. Those traces can appear as shells, faint concentric arcs in the outer light. They can appear as streams that are only visible through careful mapping. They can appear as unusual motions in a galaxy's stars. In this way, galaxies become archives of gravitational memory. Even when they look smooth at first glance, they can contain fossil evidence of encounters. And that brings us back to the idea that galaxies are long-lived patterns. A galaxy can be reshaped without being destroyed. It can lose parts and still remain itself. Even the stars stripped into a stream are not lost to the cosmos. They become part of a larger structure. They continue orbiting, carrying the imprint of the encounter. So when you think about galactic cannibalism, it can be seen as an ingredient of growth. The larger galaxy gains stars and mass. The smaller galaxy becomes a halo stream. When you think about major mergers, they can be seen as transformations. Two systems combine into one. A disk can become a spheroid. The light changes character. And when you think about starbursts, they can be seen as brief weather. A compression wave passes through the gas, and the galaxy brightens for a while. Across all of it, time is what softens the edges. A merger that is dramatic in a diagram becomes gentle in real time. A tidal tail becomes a faint stream. A starburst fades into an older population. In the next segment, we can move inward rather than outward. After the slow choreography of mergers, we can look at what often sits at the quiet center of a galaxy. We'll explore the supermassive black holes many galaxies host, and how a calm nucleus can sometimes become briefly bright. After thinking about how galaxies meet and merge, it can be calming to turn the view inward. Many galaxies have a dense central region where gravity becomes steep and motion tightens. But within that broader environment, there is another influence that sits much closer to home. It is not spread across hundreds of millions of light years. It is concentrated in the inner heart of many galaxies. In that inner region, gravity becomes steep, orbits tighten, gas can settle into rotating disks. And for many galaxies, there is an object at the center that is both ordinary in frequency and extraordinary in nature. Most large galaxies appear to host a supermassive black hole at their center. This includes spiral galaxies with bright disks and elliptical galaxies with smoother light. The black hole is not a decoration. It is part of the story of how galaxies evolve. Yet it helps to begin with a calm correction. A supermassive black hole is often quiet. It can sit in the center for long stretches of time without doing anything dramatic. A black hole does not glow by itself. If it is not actively pulling in nearby material, it can be almost invisible. Its presence is felt through gravity, not through light. Astronomers can infer a central black hole by watching how stars orbit near the galaxy's core. If stars move as if they are circling a very compact, massive object, that is a strong clue. In some galaxies, the central region also shows a tight, bright concentration that suggests deep gravitational binding. So in the calmest sense, a supermassive black hole is like an anchor. It is a small region of space that holds an enormous mass. But the anchor does not always stir the water. When the center does become active, the story changes in a way that is energetic, but still explainable without intensity. The light does not come from the black hole itself. The light comes from what happens around it. If gas drifts inward toward the center, it usually cannot fall straight down. It has angular momentum, the tendency to keep orbiting, so it forms a flattened disk around the black hole. That disk is called an accretion disk. It is a rotating flow of gas and dust that slowly spirals inward. As the material rubs, compresses, and heats, it begins to radiate energy. The key idea is simple. The gravitational energy of falling material is converted into heat and light. The black hole is the reason the energy is available, but the glowing part is the disk. When a galaxy's center is actively feeding this way, we call it an active galactic nucleus, or AGN. This phrase is not meant to be mysterious. It simply means the nucleus is bright because matter is being accreted. AGN can take many forms. Some are modest, some are powerful. The details depend on how much material is falling in and on how the system is oriented relative to us. At the most luminous end are quasars. A quasar can outshine the combined starlight of its entire host galaxy. It is not that the galaxy has no stars, it is that the center becomes an intense beacon for a time. Quasars were more common in the early universe. Young galaxies had more gas available, and interactions were frequent. Under those conditions, central black holes could feed more often and more brightly. When we see a distant quasar, we are often looking far back in time. Its light began traveling when the universe was younger. In that sense, quasars are both an energy story and a history story. It can be calming to picture a quasar as a phase rather than a creature. A galaxy does not become a quasar forever. It enters an active phase when fuel is available, and then it quiets again when the flow changes. That brings us to one of the gentlest surprises in modern observations. We do not always need millions of years to see change. Some active galactic nuclei vary on timescales that feel almost personal. Astronomers have observed quasars that brighten or dim significantly over years. Some even change their spectral appearance in a way that suggests the central engine has shifted states. These are sometimes called changing look quasars. The phrase can sound dramatic, but the idea is observational. When the flow of matter into the accretion disk changes, the light it produces can change. A thicker flow can make the system brighter. A thinner flow can allow it to fade. We can imagine it as a river whose current varies. The black hole is still there, the gravitational pull is steady, but the supply of gas is not always steady. Sometimes a clump of gas moves inward and feeds the disk more efficiently. Sometimes the inner disk changes its structure. Sometimes dust and gas shift, altering what we can see from our angle. So the flickering is not a sign of instability in the laws of physics. It is a sign that the environment near the center is dynamic. Matter flows, stalls, reshapes, and continues. This variability also reminds us that active does not always mean loud in a human sense. A quasar can be brilliant while still being distant and silent. Its light changes, but it does not roar. Another feature that can grow out of an active nucleus is even more striking in scale. Some galaxies produce jets of particles that extend far beyond the galaxy itself. These jets are often seen most clearly in radio observations. They can form enormous lobes, sometimes stretching for hundreds of thousands or even millions of light years. The galaxy becomes a source of structure far outside its visible stars. The contrast is one of the quiet wonders of astrophysics. The jets originate in a region smaller than our solar system, near the black hole and its disk. Yet they can shape regions larger than the entire galaxy. The jets do not come from inside the black hole. They appear to be launched from the environment around it, where strong magnetic fields thread the accretion disk and the spinning space near the black hole. Magnetic fields can act like rails for charged particles. When the conditions are right, they can channel matter outward along two opposite directions. The outflow becomes focused, fast, and long-lived. In images, radio jets often look like thin beams ending in broad glowing lobes. Those lobes are places where the jet deposits energy into surrounding space. The surrounding gas is stirred, heated, and pushed. This is where the idea of feedback enters. A galaxy is not just a passive home for a black hole. The black hole's activity can influence the galaxy's future. If an AGN is powerful enough, it can heat gas in the inner regions. Heated gas is less likely to collapse into new stars, so the galaxy's star formation can slow. In some cases, energy from the nucleus can drive winds that push gas outward. That gas might leave the central region entirely, reducing the available fuel for future star formation. Feedback does not mean the black hole is controlling the galaxy like a conscious agent. It means energy injected into the gas changes what the gas can do. The physics is steady, even if the consequences are large. This matters because star formation is sensitive. Stars form when gas becomes cold and dense enough to collapse. If the gas is kept warm or dispersed, the galaxy moves into a quieter phase. This is one reason many large elliptical galaxies are relatively red and dead. They contain older stars and less cold gas. Their central black holes may have had active phases long ago that helped heat or remove gas, but feedback is not always a simple shutdown. Sometimes it regulates rather than ends. Energy from the nucleus can prevent runaway star formation while still allowing some gas to cool elsewhere. It can be helpful to think of it as balance. Gravity tries to pull gas inward. Cooling helps gas settle into dense clouds. Feedback adds heat and motion that can slow the collapse. Across billions of years, this balance shapes the kinds of galaxies we see. It helps explain why the most massive galaxies are not all forming stars at high rates today. It helps explain why galaxy growth is not simply more gas equals more stars. There is also a quiet relationship between black hole mass and the galaxy around it. In many cases, more massive galaxies host more massive central black holes. The correlation is not perfect, but it suggests shared evolution. This does not mean the black hole built the galaxy alone. It means that as galaxies assembled, their centers evolved too. Gas inflows, mergers, and star formation all played roles in shaping both the galaxy and its central object. When galaxies merge, their central black holes can eventually pair up. For a time, two supermassive black holes may orbit each other inside the merged system. Over very long times, they may spiral inward and merge as well. This is another way the earlier segment connects to this one. Encounters reshape galaxies. Those reshaped galaxies carry their central black holes into new relationships. The core is part of the merger story. Yet even here, time keeps the edges soft. The pairing process can take millions or billions of years. The galaxy can look settled long before the black holes finish their slow inward drift. So if you step back, the picture is coherent. Most large galaxies host central black holes. Most of those black holes are quiet most of the time. When they feed, the accretion disk is what shines. In brighter phases, the galaxy can become an AGN or even a quasar. Some of these systems vary on human timescales, not because physics is unstable, but because the fuel supply is. And in some cases, energy from the nucleus escapes along jets and winds. That energy can heat and move gas, influencing how easily the galaxy can continue making new stars. In the next segment, we will widen the lens again. We will return to the largest patterns, how galaxies gather into groups and clusters, how they trace out filaments and voids, and how the cosmos organizes these systems into a web-like structure across immense distances and time. When you zoom out far enough, individual galaxies begin to look like points in a larger map. Their shapes and colors still matter, but another question becomes clearer. Where do galaxies tend to live, and why do they gather the way they do? The answer is not random scattering. On the largest scales, the universe has an architecture. It is subtle, but it is real, and it is one of the calmest ideas in cosmology. Galaxies follow a pattern often called the cosmic web. It is not a web made of thread in a literal sense. It is a network of slightly denser regions shaped by gravity over billions of years. In this picture, matter is not evenly spread like mist. It collects into filaments, and those filaments meet at nodes. The nodes are often where you find galaxy groups and clusters. Between filaments lie voids. These are wide regions with fewer galaxies than average. They are not perfectly empty, but they are quieter, with much lower density. A helpful way to imagine the cosmic web is to think of a three-dimensional lace pattern. The filaments are the lace strands, the nodes are the thicker crossings, the voids are the open spaces. This structure began as tiny irregularities in the early universe. The cosmic microwave background shows those small fluctuations as faint temperature variations. Gravity then amplified them over time. Regions that were slightly denser pulled in more matter. Regions that were slightly underdense became emptier by comparison. Over billions of years, the difference became a large-scale pattern. In simulations, the web looks almost organic, but the reason it forms is plain. Gravity smooths and gathers. It draws matter along paths of least resistance toward deeper wells. The filaments are not solid ropes. They are extended regions where dark matter and gas are more concentrated. Galaxies form and move along them like lights along a long road. The nodes, where filaments intersect, are where the biggest gatherings occur. Galaxy clusters can contain hundreds or even thousands of galaxies. They are bound together by gravity, and they sit in some of the deepest local wells. Clusters also contain hot gas between galaxies. This intracluster medium can glow in X-rays. It holds a large fraction of the cluster's ordinary matter, spread thin but heated to extreme temperatures. Yet even in clusters, most of the mass is not in stars or invisible gas. Dark matter dominates. It provides the main gravitational framework that keeps the cluster bound. So the cosmic web is not only a map of where galaxies are, it is a map of where gravity has gathered matter over cosmic time. The luminous parts are the visible highlights of a deeper structure. Once you picture that, another method of seeing the web becomes easier to appreciate. We cannot see dark matter directly, but we can see what its gravity does to light. This effect is called gravitational lensing. It comes from a simple idea in relativity. Mass bends space-time, and light travels along the curved paths that space-time creates. When a massive object lies between us and a more distant galaxy, it can distort the light of the background source. The distant galaxy may appear stretched, curved, or shifted. In strong lensing, the distortion can be dramatic. Light can be bent into bright arcs around a foreground galaxy or cluster. In rare symmetrical alignments, it can form an Einstein ring. An Einstein ring looks like a circle of light wrapped around the foreground mass. It is not an object shaped like a ring. It is the image of a background source, bent into a circular path by gravity. This is why lensing is sometimes called nature's telescope. A foreground cluster can magnify the background universe. It can make faint galaxies brighter and easier to study. Lensing can also create multiple images of the same background object. You might see what looks like 2 or 4 similar galaxies. In reality, you are seeing the same source along different curved paths. Even when lensing is subtle, it is useful. In weak lensing, individual distortions are too small to notice in one galaxy, but across many galaxies, the statistical pattern becomes measurable. Astronomers can map those slight distortions across wide regions of sky. From that, they can infer where mass is concentrated. This includes mass that does not emit light. So lensing turns gravity into a tool. It lets us weigh galaxy clusters and trace hidden structure. It helps confirm that the cosmic web has an invisible backbone. In a calm sense, lensing is one of the most elegant ideas in astronomy. It does not require the universe to behave strangely. It only requires light to follow curved geometry, which is exactly what relativity predicts. Now, if the cosmic web tells us how galaxies are arranged, there is another set of observations that tells us how many galaxies there are. It comes from looking at a tiny patch of sky for a very long time. In the 1990s, astronomers pointed the Hubble Space Telescope at a region that looked almost empty. It had no bright stars. It was a quiet, unremarkable corner of the sky. They left the telescope staring there, gathering light over many exposures. What appeared in the final image was not emptiness at all. It was crowded with galaxies. This became the Hubble Deep Field, followed later by the Ultra Deep Field. Thousands of galaxies appeared in a patch of sky, small enough to cover with a grain of sand held at arm's length. The lesson is gentle but profound. Even where the sky looks blank to our eyes, it is full of distant galaxies. Space is not only vast, it is populated. More recently, the James Webb Space Telescope extended this idea into the infrared. It can see objects whose light has been stretched by the expansion of the universe into longer wavelengths. The concept behind this stretching is redshift. As space expands, light traveling through it can have its wavelength lengthened. Shorter wavelengths shift toward longer ones. For very distant galaxies, this can be extreme. Light that was emitted in the ultraviolet or visible range can arrive at Earth as infrared. The universe changes the light as it travels, not by damaging it, but by stretching it. That is why infrared telescopes are so important for the early universe. The earliest galaxies are distant enough that much of their starlight reaches us in infrared. When we observe these galaxies, we are not seeing them as they are now, in some absolute sense. We are seeing them as they were when their light began its journey, so to look far away is still to look back in time. And in the deepest images, that time travel becomes almost literal. We are seeing galaxies from a universe only a few 100 million years old. Those early galaxies often look different from nearby ones. Many are smaller, clumpier, and less settled. Their structures are still assembling, shaped by rapid star formation and frequent interactions. They are also chemically younger. Early stars formed from simpler material, mostly hydrogen and helium. Heavier elements built up later through generations of stellar life and death. So when you look at distant galaxies, you are looking at the universe in a younger phase. The sky becomes a history book where each page is at a different distance. Deep fields show us that galaxy formation began early. They also show that the universe was busy. Even in the early epochs, there were already many galaxies, already growing and changing. Some of those distant sources are helped into view by lensing. A foreground cluster can magnify a tiny background galaxy from the early universe. The combination of deep exposure and natural magnification lets us see farther. In that way, the topics connect. The cosmic web creates clusters. Clusters create lensing. Lensing reveals even more of the distant universe. And behind it all is expansion. Expansion increases distances and stretches light. It also shapes what will be observable in the far future. This is a place where the idea of a horizon becomes relevant, but it does not need to feel dramatic. It is simply a geometric limit set by time and expansion. The universe has been expanding for its entire history, and the expansion appears to be accelerating. That means that over very long times, some distant galaxies will become harder to observe. Their light will be stretched to longer wavelengths. It will be redshifted and dimmed. For some regions, the expansion will eventually make it impossible for new light emitted there to ever reach us. This does not mean galaxies are vanishing in an emotional sense. It means there is a limit to communication across an expanding space. The cosmos sets boundaries on what any one location can see. In the present era, we live at a time when the universe is unusually readable. Light from a great range of distances can still arrive. We can still see deep into cosmic history. So the cosmic web is not only a structure in space, it is a structure in time. It is the pattern that grew from early fluctuations into filaments and clusters, and it is the pattern that deep field images reveal across billions of years. And gravitational lensing is one of the tools that ties these ideas together. It lets us trace hidden mass, map large-scale structure, and glimpse galaxies that would otherwise be too faint. If you let one calm image remain from this segment, it can be this. Imagine the universe as a dark, wide ocean with gentle currents. Along the currents, matter gathers into threads. Where threads cross, bright cities of galaxies form. Between them, there are quiet spaces. And across the whole scene, light travels patiently, sometimes bent by gravity, sometimes stretched by expansion, always carrying information from the past. In the final minutes, we can let this panorama settle into a simple perspective. Galaxies are not isolated decorations scattered in emptiness. They are part of a connected architecture shaped by gravity, revealed by light, and unfolding over time. And as the details soften, the larger pattern can remain. A universe that is vast but structured. A sky that looks still but is filled with history. and galaxies tracing that history quietly, one distant glow at a time. If you step back from that last image, one thing becomes clear. A galaxy is not a finished object that sits still in space. It is a process that keeps unfolding at a pace so slow that it can look permanent. Galaxies grow not only by forming new stars, but by gathering material and by merging with companions. They reshape themselves under gravity, settle into new patterns, and sometimes change their entire form. What we call a galaxy is a long-lived balance, not a frozen sculpture. Even when a galaxy looks calm in a photograph, it is full of motion. Stars orbit the center, gas drifts through spiral arms. Dark matter holds the outer regions together with an influence we feel, even when we cannot see it. Over time, that motion becomes history. A faint stream of stars can mark an old encounter. A rounded, smooth glow can be the final shape after many mergers. A quiet red population can be the memory of a galaxy that once formed stars more quickly. So as this episode comes to a close, the most helpful perspective may be the simplest. Galaxies are not separate facts. They are chapters in a single story of gravity and time. If you let that story return as a few calm images, it can feel almost like a slow collage. You might picture a spiral galaxy from above, arms curved like a gentle pattern, gas and dust tracing the places where new stars can still appear. You might picture an elliptical galaxy as a soft, steady haze with stars moving in many directions, not in a single ordered plane. A shape that looks quiet because its most dramatic changes happened long ago. You might picture a dwarf galaxy, small and fragile, drifting near a larger host. Not as a minor detail, but as an important piece of how big galaxies grow, one quiet addition at a time. And behind all of these visible shapes, you can imagine the invisible halos, wide, extended regions where dark matter dominates the mass, a hidden framework that keeps galaxies bound and helps guide where gas can settle and where stars can remain. If you picture the cosmic web again, it can be even simpler now. Filaments like faint highways, nodes like gatherings, voids like wide, low-density quiet. A structure that exists whether we name it or not. In that web, clusters form, and within clusters, galaxies move through hot, thin gas. Some lose their own gas and grow quieter. Some collide and merge. Some are bent and stretched by tides, leaving long trails that fade slowly into the dark. And above all of it, there is light traveling through space with no need for drama. Some light is nearby from familiar stars. Some light is ancient, arriving from galaxies whose photons began moving long before Earth existed. When the light comes from very far away, it also brings time with it. Distance becomes a gentle kind of archive. The farther the glow, the earlier the chapter, and the more the universe is revealed in its younger forms. This is why facts about galaxies can feel restful, even when they describe things of enormous scale. The rules are steady. Gravity gathers, motion balances, light carries information. The universe is vast, but it is not arbitrary. And it can help to remember where we are inside that structure. We are inside one galaxy, not outside of all of them. We live within a spiral system of stars, gas, and dust, held within an invisible halo. That galaxy is not alone. It belongs to a local neighborhood, a group of galaxies bound together by gravity. Some are large companions, many are small dwarfs, faint and easy to miss without careful observation. And beyond that neighborhood, the group belongs to a larger gathering of groups and clusters. Those gatherings trace filaments, and the filaments trace the web. What feels like the universe from a human scale becomes, in astronomy, a pattern of nested structures. It can be calming to see that nesting clearly. A planet within a solar system within a galaxy within a group within a larger web of matter and time. Nothing about that picture requires urgency. The timescales are so long that change becomes soft. Mergers take hundreds of millions of years. Star formation rises and falls over eras. Filaments evolve across billions of years. Even the bright moments, like a quasar phase, are temporary in the life of a galaxy. They flare when fuel is available, and then they settle again. The universe has bursts and lulls, but it does not rush. So as you let the ending arrive, you do not need to hold every detail. It is enough to keep the general sense of order. Galaxies as processes shaped by gravity, connected by structure and revealed by light. A spiral arm is not only a shape, but a moving pattern. An elliptical glow is not only a color, but a history. A halo is not only an idea, but a necessary part of how galaxies stay bound. And the cosmic web is not only a metaphor, it is the calm result of gravity working patiently across a universe that began with small irregularities and expanded into a vast, structured sky. If you return to the night sky now, it can feel deeper than before, not just a scattering of points, but layered distances, not just a backdrop, but a record. Some of what you see is close, some of it is far, and beyond what the eye can detect, there are galaxies in every direction, moving slowly, evolving quietly, and holding their shapes for spans of time that are difficult to imagine. For tonight, it can be enough to let that thought be gentle. We are inside the story, not separate from it. And the universe, in its immense scale, still follows simple rules. A vast structure, a quiet motion, old light crossing space, and galaxies growing and settling as part of the larger pattern that holds them all. Good night.